Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes its time. Whether you're winding down for the night or just letting your mind wander a little before sleep, I'm glad you're here. Tonight, let's follow a question. Not one with easy answers or neat edges, but one that invites us to think differently about the ground beneath us. What if Earth was designed? Now, I don't mean designed as in picked off a shelf or assembled like a flat-pack bookshelf, although the idea of tiny cosmic tools is admittedly fun to imagine. I mean the broader idea. What if Earth wasn't just the result of random events and blind physics, but something shaped, intentionally, methodically, by some force or process? Whether you picture that as an intelligent creator, a complex simulation, a vast natural algorithm, or something else entirely is up to you. The point is, we're going to explore this not as a debate, but as an exploration. No loud opinions here, just quiet questions. And we won't be rushing to answers. That's not the pace we keep around here. Instead, we'll take a slow walk through the landscape of the idea, noticing the small details and the big patterns. And maybe along the way, we'll discover that even asking the question opens new ways of seeing the world, ways that are just as important as the answer, if not more. To begin, let's start small. Not with physics or philosophy, but with the simple personal experience of looking around. Think about your ordinary day. You wake up to light pouring through your window, not too hot, not too cold. You breathe in air that your body is perfectly built to use. You get thirsty, and water, clear, tasteless, essential, is there, waiting. Maybe you go outside. Plants, animals, sky, temperature, gravity. Everything seems to line up in just the right way to make life not only possible but comfortable. It's easy to take that for granted. Most of us do. But under that comfort is something worth pausing over. Is it all coincidence? Could it be? Or is it arranged, like pieces in a puzzle that just happen to fit a little too well? Of course, science has offered a detailed, well-evidenced story of how Earth came to be the way it is. There's no shortage of information on the early solar system, planetary formation, chemical evolution, and so on. We've built models, gathered data, and traced timelines that stretch billions of years. It's a robust framework. And yet, even within that framework, there are things that make people pause, things that seem, frankly, a bit too convenient. Earth orbits a very stable star. It does so in a range that's often referred to as the habitable zone, a zone where water can exist in liquid form, which turns out to be pretty important for life as we know it. That alone might seem fortunate, but it goes further. The planet's tilt, which gives us seasons, its rotation speed, which keeps temperatures from swinging wildly, a size of the moon, which affects tides and stabilizes that tilt, the presence of a magnetic field that shields us from solar radiation, the mix of gases in the atmosphere, the balance of land and ocean. You can keep going. Each of these things could have been different. Wildly different. And if they were, life as we know it might never have appeared. Some call this the anthropic principle. The idea that, of course, the universe looks suited to life because we're here to observe it. If it weren't suited to life, we wouldn't be around to ask these questions in the first place. It's a tidy explanation in one sense, but it doesn't stop the wondering. Is it really enough to just say, well, we're here, so it must have worked out somehow? Or is that dodging something deeper? Now, none of this proves design. That's important to say. Patterns don't prove purpose, but they can point to it, or at least make it worth considering. So what we're going to do is look at these patterns, not as believers or skeptics, but as explorers. We'll wander through the clues and coincidences, the physics and the philosophy, the math and the metaphors, and we'll do it slowly without needing to land on a single conclusion. Because whether Earth was designed or not, it behaves in ways that often feel as if it was. That's not a claim, it's just an observation. An invitation, really, to ask, what would be different if it were designed? What would stay the same? To explore this, we'll need to go wide and deep. We'll talk about planetary physics, of course, and biology and chemistry. But we'll also talk about perception and narrative, and why humans are so drawn to the idea of a world made with intention. Some of that might come from religion, sure, but not all of it. The urge to look at the sky and feel that it means something is older than any book or temple. It might be something built into us. Take, for example, the way we interact with symmetry. We're drawn to it. Faces, flowers, shells, galaxies. When we see symmetry, our brains light up. It feels right. That preference isn't proof of anything, but it's a starting point. Why should a universe formed by randomness keep giving us order? Why does our sense of beauty so often align with what turns out to be efficient, functional, and mathematically elegant? This is where things get interesting, because even if you start from a purely scientific worldview, you still end up swimming in questions that sound philosophical. The more we learn about biology, for instance, the more we realize how incredibly fine-tuned many systems are. From the way proteins fold, to how DNA stores information, to the way cells communicate, it's all precise, interdependent, and in many cases, inexplicably efficient. Not perfect, certainly. Evolution is messy, and the body is full of quirks and leftovers. But it works astonishingly well, and it works in ways that sometimes resemble what we might call design. Now, design is a loaded word. It tends to bring up images of a conscious being sketching blueprints or tweaking molecules. But it doesn't have to mean that. It can also mean structure, intention, pattern that arises not randomly but with direction. Even if we don't know the source of that direction, the idea that Earth is designed doesn't require a specific designer. It might mean something more abstract, like a universe governed by deep logic that just happens to yield life-supporting outcomes. Or it could mean something else entirely. There's also the possibility that Earth wasn't built from scratch, but selected. Out of many possible worlds, this one happened to support life. And so, here we are. But that raises another question. How many possible Earths are there? Are we just the lucky one in a trillion? Or is the universe teeming with other worlds like this, each with its own version of stability and strange beauty? We don't know yet, but as we start to discover exoplanets, and we've found thousands, we're beginning to see just how rare or common Earth-like conditions might be. So far, nothing quite matches what we have. We've found planets that are too hot, too cold, too big, too dense, too exposed to radiation, or too young. Planets without atmospheres, planets with too much gas, planets that orbit stars that flare violently. The more we look, the more it becomes clear that Earth is unusual. Not impossible, not singular, but certainly not average. And yet, average is hard to define in a universe this big. Maybe the rarity of Earth-like conditions is exactly what we'd expect in a system governed by chance. Or maybe it suggests something else. Either way, it invites us to keep asking. Another interesting point to consider is time. Not just space, not just location in the galaxy, but timing. Life didn't just need the right ingredients, it needed the right sequence. A stable planet, yes, but also billions of years of relatively calm cosmic weather. Not too many asteroid impacts, not too many solar flares, a moon to help stabilize, tectonic activity to recycle carbon, an atmosphere that gradually changed in exactly the ways life required. The timing had to line up. That's not impossible, but it's another piece in a growing puzzle. People have tried to explain this in many ways. Some see it as divine, others as luck, others as inevitable given enough time and space. But the idea that Earth might have been intentionally arranged, either directly or through some deep structure of natural laws, remains compelling. Not because it's provable, but because it continues to align with our lived experience. We are creatures who build things, who plan, who imagine outcomes before they happen. So when we look at a world that seems built just so, it's natural to wonder if something so It's natural to wonder if something or someone planned it. Still, we have to be careful. Patterns can emerge from randomness. Perception can mislead. Just because something feels designed doesn't mean it is. Just because it's unlikely doesn't mean it was planned. But the flip side is also true. Just because science can explain how something happened doesn't mean we fully understand why it happened, or whether there's a deeper structure behind it. So the question we're exploring isn't about disproving science or proving belief. It's about holding a space where both can ask the same question from different angles. What if Earth was designed? What changes? What stays the same? And what, if anything, does that mean for how we live, how we see each other, and how we move forward? As we continue, we'll start looking at specific aspects of Earth that often come up in this conversation. The orbital sweet spot, the moon's uncanny role, the surprising balance of the atmosphere, the strange details of DNA, the many systems that had to align for intelligent life to emerge. Each of these opens up its own set of questions, not only about science, but about what we expect from reality itself. When we ask whether Earth was designed, we're not just wondering about planets or physics. We're brushing up against something deeper. This question, underneath all its science and speculation, is actually very personal. It's about how we understand our place in the universe. Whether we think life is an accident that just happened to work out, or something more deliberate. Whether we see the world as a series of coincidences, or part of something that was meant to be exactly as it is. That's why this idea feels different from other scientific topics. If you ask how volcanoes form or why seasons change, it's interesting, but not emotional. But when you ask if Earth might have been made on purpose, you're stepping into a much older conversation, one that goes back long before telescopes or textbooks. You're asking a question people have been asking since they first looked up at the stars and wondered what all this is for. It's the kind of question that shows up in philosophy, in religion, in mythology. Stories about the Earth being shaped by hands or spirits, or voices that spoke the world into being. And while many of those stories conflict with each other in the details, they share something important. They reflect a human instinct, the urge to connect what is with what means, to turn facts into purpose. That instinct isn't something we should dismiss. It's easy to assume that science and meaning are separate, that one tells us how and the other tells us why, but the line isn't always so clean. The more we understand about how the universe works, the more we notice moments where structure and outcome seem to converge in ways that feel, for lack of a better word, guided. Take something as basic as carbon. Life on Earth, at its core, is built around this one element. Carbon forms the backbone of DNA, proteins, and all the complex chemistry that makes cells go. It's incredibly versatile. It bonds easily, it forms long chains, it creates stable molecules that can carry information and build structure. Without it, life as we know it simply wouldn't work. And when you look at how stars create elements, you realize that carbon itself is the product of a very narrow set of conditions. If the physics of fusion were just slightly different, slightly stronger or weaker, the universe might be full of hydrogen and helium, but no carbon. No carbon, no life, no us. That kind of coincidence makes people stop and think. Not because it proves anything, but because it shows how specific things had to be. And the more we learn about the laws of physics, the more it seems like a lot of these values, mass, charge, gravity, the strength of forces, had to be within very tight ranges for complex matter to exist at all. Not just life, but stars, planets, chemistry. That's sometimes called fine-tuning. And it raises a question that sits quietly behind so much of modern science. Why these numbers? Why this version of reality? There are ways to explain it. One is the multiverse. The idea that maybe there are countless universes, each with its own set of physical constants, and we just happen to be in the one where everything lines up. That could make sense. But we don't have any direct evidence for other universes. Not yet. And even if we did, that still wouldn't tell us why our universe exists the way it does. It just pushes the question back a step. Another idea is that maybe these values aren't selected at all. Maybe they're just built into some deeper structure we haven't found yet. But that's still a kind of mystery. Because either way, we're looking at a reality where things had to be a certain way, and they are. And then, inevitably, you arrive at the deeper version of the question. Not just why is the Earth the way it is, but why is anything the way it is? Why do the laws of physics exist at all? Why should there be a universe with rules and structure and patterns and matter? Why should there be something rather than nothing? That's a question no telescope can answer. And yet, we keep coming back to it. Now, it's important to say, science doesn't need purpose in order to work. You can study gravity without believing it was created. You can decode DNA without asking who wrote it. But science doesn't forbid those questions either. It just doesn't depend on them. And for some people, that leaves space for a kind of middle ground, a place where you can explore the world through evidence and still leave room for the possibility that there's more going on than we can measure. This is where design enters the conversation, not as a replacement for science, but as a perspective, a lens. It doesn't say that we should stop asking questions when something seems fine-tuned. It says the fine-tuning itself is worth noticing. And maybe, just maybe, it points to something deeper. Of course, not everyone agrees on what that deeper thing might be. Some people picture a conscious designer, a god, an architect, a being with intentions. Others imagine a kind of built-in intelligence to the universe itself. Not a person, but a process that naturally tends toward order, beauty, or complexity. Others see design as a human projection, something we impose on the world because we're wired to find patterns and stories. In each of these views, the question is the same, but the answers differ. Even so, the question stays. It sits there, quietly, behind everything we do. Every scientific discovery, every new image from a satellite, every equation or theory, all of it is framed by this strange fact. That we are here, looking, that there's something to look at, and that it behaves in ways we can understand. Think about that for a moment. Not just that the world exists, but that it's intelligible, that we can measure it, predict it, explain it, that our brains, which evolved from ancient nervous systems designed to find food and avoid danger, can now model galaxies, build computers, and ask whether the universe has a purpose. Why should the mind of a species on a small rock in a remote corner of a galaxy be able to grasp the rules that govern space and time? Again, that doesn't prove anything, but it's odd. It makes you wonder whether our ability to understand the universe is itself part of some larger pattern. Whether the universe is not only structured, but structured in a way that invites understanding. That's not a claim, just a thought. In the end, these questions don't have to be threatening. They don't take anything away from science. If anything, they show how science can lead us right up to the edge of mystery and then keep going. You don't need to answer every question in order for it to matter. Sometimes just holding the question is enough. And this one, this idea that maybe the world was built, arranged, or shaped in some way, is one of the oldest questions we have. But it's also one of the most modern, because now we have the tools to look more closely than ever, to explore the building blocks of matter, the forces of nature, the dynamics of life. And as we do, the question only deepens, not because we're running out of explanations, but because the explanations themselves are so detailed, so precise, and so delicately balanced that they make you pause. They make you think, is this all just what happened to work, or is it what was meant to happen? We can't answer that fully, not yet, maybe not ever. But we can keep asking. We can keep following the structure, the order, the logic. Not to prove anything, but to understand, and maybe in the process get a little closer to what lies at the heart of it all. When we start looking closely at Earth itself, not just its place in the cosmos, but its surface, its system,
we start to notice certain patterns. Some are geological, some are chemical, some are mathematical, and some are structural. And the more we zoom in, the more those patterns can start to feel oddly intentional. It starts with the basics. The planet's crust, for instance, is divided into plates. These plates float on a hotter, softer mantle layer, shifting over time. This movement creates mountains, earthquakes, volcanoes, and even oceans. Without plate tectonics, the Earth's surface would likely be flat and static. Erosion would wear it down. Nutrients wouldn't cycle. Life, as we know it, might never have flourished. The movement of the plates also plays a role in regulating carbon. When volcanoes erupt, they release CO2. When mountains weather, they draw CO2 back down. That balance affects the climate, which in turn shapes the entire biosphere. Now that's a process science has mapped out in great detail. But when you look at it from a wider angle, it's hard not to wonder how many ways that system could have failed. The planet didn't just need a solid crust. It needed one that cracked, floated, and moved. If the crust had been too thick or the mantle too stiff, the plates wouldn't shift. If it had been too active, the surface might be constantly remade, leaving no time for life to stabilize. Somehow, Earth landed in the middle, not too calm, not too chaotic. The more we look at how things are arranged, the more this middle ground idea comes up. Soil, for example, is a mixture of minerals, organic matter, water, and air. But the ratio has to be just right. Too much sand, and water drains too quickly. Too much clay, and roots can't breathe. The best soils, the ones that grow forests, crops, and ecosystems, strike a careful balance. That balance can vary by region, but it's always within a narrow band of properties. Plants evolve to match those conditions, or maybe the other way around. That's a theme that comes up a lot: coevolution. Not just plants and soil, but insects and flowers, fungi and trees, bacteria and animals. Systems that don't just work, but work together, each part shaped by the presence of the other. And sometimes the fit is so exact that it starts to feel more like assembly than adaptation. Consider something as ordinary as a seed. It contains everything it needs to grow: the instructions, the energy, the structure. It waits in the soil, responding to moisture, temperature, and light. When those conditions line up, it transforms. Roots stretch downward, stems reach upward. It's a process we can describe in biological terms, but the timing, sensitivity, and precision involved are striking. Even the shape of seeds, the way they travel, stick, sink, or float, seems optimized. Not perfectly, but very effectively. It's easy to see all of that as the result of natural selection. Traits that worked survived. Traits that didn't faded away. But selection works on what's available. It doesn't build from scratch. It repurposes, adjusts, trims. So the starting materials matter. And when we look at those starting materials, the building blocks of life, carbon, nitrogen, oxygen, hydrogen, they're not just common, they're unusually versatile. They bond easily. They store energy well. They form the right kinds of molecules, the kinds that loop and twist and replicate. Some of that may be chemistry, but chemistry too follows rules. And those rules, in our universe, seem to lean toward complexity. That doesn't mean complexity is inevitable, but it does mean that once it starts, it has room to grow. And Earth, for whatever reason, seems to have given it a head start. Take water. It's not a metal or a gas or a particularly rare compound, but it has a list of unusual properties. It expands when it freezes, which means ice floats, a rare trait that allows life to survive under frozen lakes. It has a high specific heat, which stabilizes temperature. It dissolves more substances than almost any other liquid, making it the perfect medium for chemical reactions. All of those traits just happen to be ideal for life, and all of them come from the angle between two hydrogen atoms and an oxygen atom. If that angle was slightly different, water would behave completely differently, and so would everything that depends on it. Then there's the idea of fractals, patterns that repeat at different scales. You see them in river networks, mountain ranges, coastlines, tree branches, blood vessels. These aren't just pretty shapes, they're efficient. They move resources across large areas with minimal material. Trees send nutrients from roots to leaves using fractal branching. Our lungs do the same with air. These forms aren't random. They follow specific mathematical rules. Rules that keep showing up independently in different systems. Some call that convergence. Others see something more deliberate. Another example is the Fibonacci sequence, the spiral pattern found in shells, pine cones, sunflowers, galaxies. It's not universal, but it's common, and it often shows up where growth is involved. That's because it allows for efficient packing and expansion. Again, there's a mathematical reason behind it, but the fact that math shows up in biology at all is worth thinking about. That living things, shaped by blind processes over millions of years, often align with principles we find elegant or logical. It raises an odd question. Does the universe follow math because it has to? Or does math describe it so well because both come from the same source? That's not just a philosophical puzzle. It has real implications for how we understand structure. Because if life arises from patterns, and those patterns follow rules, then where do the rules come from? This is where the idea of blueprints comes in. Not in the literal sense of someone drawing up schematics, but in the sense of consistent systems that create outcomes. The Earth isn't random, and it isn't purely chaotic. There's order here, a kind of layered functionality. From soil chemistry to planetary motion, things behave in regular, testable, repeatable ways. That's what science depends on. But it's also what makes people wonder whether that regularity points to something behind it. Patterns can come from chaos. That's true. We've seen it in simulations and models, but those patterns often require very specific initial conditions. Tweak them slightly, and the outcome changes completely, which makes you wonder, what were the initial conditions here? Why these laws? Why this structure? Why a world where minerals form crystals, plants respond to light, and animals can evolve eyes? That's not to say anything supernatural is going on. But the more we examine the structure of Earth, the blueprints in its soil, its systems, its cycles, the more the question keeps coming back. Could this have been arranged? Not by magic or miracle, but by a process we don't yet understand. One that includes design, not as a product of choice, but as a principle. A natural tendency towards systems that support life. We don't have to decide that now. We're not here to answer, only to notice. And what we're noticing is that Earth is not a random mix of stuff. It's a deeply interconnected system, full of rules, balances, and alignments that seem to lean towards stability, growth, and resilience. That doesn't mean it's perfect, far from it, but it works, and it works in ways that feel oddly tuned. When people talk about why life exists on Earth and not on Mars or Venus, they often mention something called the Goldilocks zone. It's a nickname for the area around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist. And since water seems to be necessary for all known forms of life, the assumption is that any planet sitting comfortably in this zone has at least a fighting chance. Earth sits right in the middle of that range, close enough to the sun to avoid freezing, far enough to avoid boiling. The sun itself is stable and long-lived, giving the planet billions of years to develop complex ecosystems. It's easy to hear that and feel a kind of satisfaction, like the universe played a very specific game of darts and landed right on the bullseye. But as usual, the closer you look, the more complex it gets. The habitable zone isn't fixed. It depends on the size and brightness of the star. A smaller, dimmer star has a tighter, closer in Goldilocks zone. A larger, hotter star pushes the zone farther out. That might sound like a wash, but each case brings its own complications. Smaller stars tend to flare, sending out blasts of radiation that can strip away a planet's atmosphere. Bigger stars burn through their fuel faster, meaning less time for life to evolve. Earth's sun, it turns out, is just about average, stable,
Bright and long-lived. It may not be the only kind of star that can support life, but it's one of the better ones. Then there's the orbit. Earth doesn't just sit at the right distance, it stays there. Its path around the sun is nearly circular. That means the amount of solar energy it receives doesn't vary wildly throughout the year. Some variation is useful, that's what gives us seasons. But too much would make the climate swing between extremes. A slightly more elliptical orbit could have made the planet uninhabitable in large regions. And yet, here we are, with a wobble that's not too sharp and a tilt that's just enough to stir things up without throwing everything off. Still, distance and orbit are just the beginning. A planet can sit in the habitable zone and still be completely sterile. Just look at Mars. It's in the outer edge of the Goldilocks range. It has ice. It may have had water in the past, but it's dry now and cold and exposed to radiation. The reason? Its magnetic field collapsed, and with it, much of its atmosphere was lost. No shield, no pressure, no warmth, no protection. The ingredients were there, but the kitchen fell apart. Venus is on the other end, just inside the inner edge of the habitable zone. It's about the same size as Earth and has a similar composition. But its atmosphere is thick with carbon dioxide, creating a runaway greenhouse effect. Surface temperatures are high enough to melt lead. Its clouds are made of sulfuric acid. If Earth is a warm cup of tea, Venus is a boiling kettle that never stops screaming. This puts Earth in a very small window, not just in terms of distance, but in how its systems work together. Its atmosphere is thick enough to trap some heat, but not too much. It contains oxygen, nitrogen, and carbon dioxide in just the right mix. Its oceans moderate the climate. Its weather systems distribute heat around the globe. The greenhouse effect exists but doesn't run out of control. For now, it's not a delicate balance exactly, more like a dynamic one. Things shift, adjust, compensate. When something changes, other parts respond. That flexibility is part of what makes the system stable. But again, it didn't have to be this way. Small differences in early conditions could have led to a planet that looked very different. And if you rewind far enough, you get to the formation of the solar system itself, the swirling cloud of gas and dust that gave birth to the sun and its planets. In that cloud, where Earth ended up was determined by a mix of gravitational pulls, collisions, and leftover materials. It could have formed farther out, where it would be a frozen rock. It could have formed closer in, where it might have ended up like Mercury. But it didn't. It formed here, in the zone where water could stay liquid, and life had the time and conditions to begin. Some see that as chance, the result of many rolls of the cosmic dice, and that's a valid perspective. But others look at the outcome. A planet with just the right temperatures, just the right chemistry, just the right history, and wonder whether the dice were loaded, not in a rigged or unfair way, but in a way that suggests direction. Maybe not intentional, but not indifferent either. That line of thinking leads to more questions. Is the Goldilocks zone a unique feature or a common one? Do other stars have planets in the right range? As it turns out, yes, at least in theory. Thousands of exoplanets have been found, and quite a few lie in their star's habitable zone. But we don't know much about them yet. We don't know if they have atmospheres, water, or magnetic fields. We don't know if their climates are stable or violent. We don't know what's going on beneath the surface. And even if one of them has the right ingredients, we don't know if those ingredients have formed life, or if life ever got the chance. So Earth remains our best example, and the more we study it, the more finely tuned it seems. Not perfectly. Climate can shift. Natural disasters can occur. Ecosystems can collapse. But overall, the balance holds. Life persists, and not just simple life. Complex life, conscious life, life that asks questions about how it all came to be. The phrase "just right" can sound simple, but it isn't. It includes hundreds of interacting systems: geology, weather, magnetism, chemistry, biology. all behaving in ways that support the presence and continuity of life. It's not just the location, it's everything the location allows. And still, that might not be enough to prove anything. Maybe it's a lucky outcome. Maybe life is rare but not impossible. And Earth is simply one case where things happen to line up. That's the standard scientific view. There's also a quiet, persistent sense, not a conclusion, but a feeling, that this lining up goes beyond odds, that it reflects something deeper about how the universe works, or wants to work. If we assume design, what would that design be aiming for? Life, maybe, or complexity, or perhaps just balance. A system that holds itself together long enough to become interesting. That doesn't mean everything is good or easy. Earth isn't a utopia, but it is unusually well positioned for something rare and complicated to happen. Once you start looking beyond where Earth is and start focusing on what Earth is, the structure of the planet itself becomes part of the story. Not just the surface or the land masses we walk on, but the full layout, from its iron core to the shape of its orbit. If Earth was meant to support life, you'd expect that structure to be part of the plan. And even if it wasn't designed in any purposeful way, the arrangement of its parts still raises some interesting questions. A lot of this starts at the center. Earth's core is made mostly of iron and nickel, and it's divided into two parts, a solid inner core and a liquid outer core. The movement of that outer core is responsible for creating Earth's magnetic field, which shields the surface from solar and cosmic radiation. Without it, the planet would be constantly bombarded by charged particles that could strip away the atmosphere, damage DNA, and make life a lot harder, if not impossible. That magnetic field doesn't just exist. It's generated through a process called the geodynamo. The Earth's rotation causes the liquid metal to swirl, and those movements generate electric currents, which in turn create the magnetic field. For that system to work, a few things have to be in place. You need the right materials. You need a certain amount of internal heat, which comes from radioactive decay and leftover energy from the planet's formation. You need a certain size, because smaller planets cool too quickly. You also need rotation, but not too much. Earth spins once every 24 hours, which is fast enough to keep the core moving and stable enough not to cause chaos at the surface. It's easy to take that for granted, but change any of those pieces. Make the planet a little smaller, a little slower, a little less metallic, and the whole magnetic system could fail. That's what happened with Mars. It likely had a magnetic field early on, but it cooled too fast, the core stopped churning, and the shield disappeared. What followed was the slow loss of its atmosphere and surface water. Above the core is the mantle, which moves slowly over time, driving the tectonic plates on the surface. Those plates, as we talked about earlier, are crucial. They're involved in recycling minerals, shaping continents, building mountains, and regulating the carbon cycle. But they also require a certain amount of heat and a delicate balance between rigidity and movement. If the mantle were too soft, the crust would break apart constantly. Too stiff, and nothing would move at all. Earth seems to have landed on the right settings. It's dynamic, but not unstable. Over time, continents drift, collide, break apart, and reform. That movement changes climate, creates new environments, and helps isolate ecosystems, a key driver of biological diversity. It's also part of why so many different forms of life evolved in different regions. Without that movement, the planet's surface might be uniform and stagnant. Even the crust itself plays a role. It's thin compared to the rest of the planet. Just a few kilometers deep under the oceans, a bit thicker under the continents. It's where all surface life exists. The composition of that crust is rich in the elements life needs. Carbon, phosphorus, sulfur, calcium, potassium. Those elements didn't all come from Earth's original materials. Many arrived during a phase called the Late Heavy Bombardment, when asteroids and comets delivered organic molecules, water, and other building blocks. That event could have gone very differently. Too many impacts, and the surface might never have cooled. Too few, and maybe the planet wouldn't have the ingredients life needed. Instead, Earth seems to have received just enough, a mix of rocky and icy objects that added to what was already there. Another moment where things didn't have to line up but somehow did. On the outside of all that is the atmosphere, which acts as both a barrier and a support system. It keeps the planet warm, protects it from smaller space debris, and contains the gases necessary for respiration and photosynthesis. But it didn't start out that way. The early atmosphere was likely full of carbon dioxide, methane, and ammonia, toxic to modern animals but useful for early microbes. Over time, photosynthetic organisms began producing oxygen, which eventually transformed the atmosphere into what we have today. That change, known as the Great Oxygenation Event, could have gone either way. Oxygen is reactive. It can be harmful in high concentrations, but in the right amounts, it allows for complex metabolism, which in turn supports multicellular life. The fact that Earth's systems didn't collapse under the strain of that shift is another example of how feedback loops, both positive and negative, kept things within a certain range. The balance between carbon dioxide and oxygen is still being managed by living systems. Forests, oceans, and soil act as carbon sinks. Volcanic activity and respiration add gases back into the mix. The result isn't perfect equilibrium, but a system that self-adjusts, at least over long time periods. In that sense, Earth's surface is less like a machine and more like a living organism. Responsive, flexible, always adapting. And then there's water. Its distribution isn't even, but it's effective. About 70% of the surface is covered in oceans, which help regulate temperature and circulate nutrients. Fresh water exists in rivers, lakes, ice, and underground aquifers. That mix supports both marine and terrestrial life, and it relies on a planetary system of rainfall, evaporation, and flow that's tied to both geography and solar energy. Even the tilt of the planet, about 23.5 degrees, shapes how sunlight hits different regions, creating seasonal cycles. That tilt is stabilized by the moon, which we'll look at in more detail next. Without it, the tilt might wobble chaotically, causing wild shifts in climate over short periods. Instead, we get a reliable rhythm that life has adapted to. Migrations, hibernations, flowering times, all timed to the angle of sunlight and the arc of the year. Pull all these pieces together, and what you get isn't a simple object in space, but a complex layered system. One that generates its own magnetic field, regulates its own temperature, cycles its own resources, and hosts its own life. A planet that builds the conditions it needs and maintains them through feedback and flow. None of that proves anything beyond what we observe, but opens up a different way of looking. Instead of seeing Earth as just a lucky combination of traits, you might start to see it as something with internal logic. Not logic imposed from outside necessarily, but logic that leads to life-supporting outcomes.